I clearly understand that we are near lunchtime and that you're very tired, but I hope this lecture will be interesting for you. We are just switching everything. We will not talk about particle physics. We will not talk about gamma rays or, let's say, high energy particles. In this talk, we will speak about X-rays and the application of X-rays using as a source synchrotron radiation. Why did they ask me to give this talk today? Because they probably told you this is the International Year of Light. And there are a lot of things that are important this year because we are, it's about 1,000 years after the first publication of studies about optics that was done in 1015. Then we have also the discovery that light is also wave, can be considered as a wave. Then we have the theory of light from Maxwell. And then there is the general theory of relativity from Einstein, and so on. So there are a lot of reasons why to decide that 2015 is the International Year of Light. When we speak about light sources, we intend something normally in our normal life is something that gives us the chance to see something with our eyes, okay? Here you have two different kinds of light sources. Funziona?
Sì, prova. Prova, prova. Sorry. Okay, now it's possible. You hear me? Okay. So, if we use fire, think to be in the darkness, okay? You have your torch of fire and you move around. Since fire has not a, let's say, a defined direction, but it's emitted in all around you, it's not easy to see details. If you want to see details, the best thing is to use a light torch. Probably you can orientate your light torch in a certain direction, and you can see also things far away from you. But if I don't want to limit myself only to things that I can see with my eyes, but I want to study things that I cannot see with my eyes, I can use other kind of sources like synchrotron radiation that gives me a very powerful beam that goes from infrared up to X-rays. And I can use X-rays to study things that I can normally not see with my eyes. Speaking of visible light is a very tiny slice of the whole electromagnetic spectrum. Oops, it's up here, okay. You see, this one goes from radio waves up to gamma rays. And the part related with visible light is very tiny. It goes from 380 nanometers up to 780. But what is the importance of this part? This is important for us because with our eyes, we can select the different wavelengths and distinguish colors. I'm red, you're black, and so on, because we have eyes, and our retinas are able to distinguish these different wavelengths, okay? When I speak of wavelengths, I speak of the distance between the top point of two waves. And what you can see here is that also in visible light, when you move from red to blue, you're changing the wavelength. This one is bigger in red light, but becomes smaller and smaller as you move from red to blue. And so look at this other picture. This is the central part where we have the visible light. But if you move from visible light to X-rays or gamma rays, you see that what is changing is this wavelength. It becomes smaller and smaller. And as I will show you after, when I decrease the wavelength, I increase the frequency. And with the frequency, as you heard this morning, you increase the energy. Okay, so if I want to study atoms whose dimensions are around 10 to the minus 10 meters, I cannot use visible light. I need to use wavelengths that have a dimension comparable with the things I want to study. okay? So to study atoms, I use X-rays. Atoms are, make everything, we are done of atoms. Where you're sitting is done of atoms, your computers are done of atoms, everything. Also the air we breathe are atoms. So they're very important. And this table is interesting because with about 100 elements, we do all the things that surround us. Okay, so study atoms is very important. I don't know if you ever thought about this. Here you have a gold bar. With gold, you can make coins. But inside your coins, you have all these small atoms organized following a specific structure. So your question could be, but why I am interested in the structure of atoms? This is the reason why. All the chemical, optical, physical properties of materials are related to their structure. And I will show you this example that is very interesting. Here you have graphite and diamond. Did you ever think in your life to write something using a diamond? Or cut something with your pencil? No, why? You're speaking of two materials, both made of carbon. But what changes? The thing that changes inside these elements is the structure. In diamond, you have these carbon atoms organized using a tetrahedral structure that is very strong and hard. In graphite, you have layers of graphene tied one to the other with very weak forces called van der Waals forces. So when you write, what you do is you just release on the paper layers of graphene. Okay? So we write with pencils, and we cut things with diamond because diamond is very hard. Why? So we understood now that X-rays are important to study the structure of materials. But the structure of materials has a very wide range of application fields. It can be important for chemistry, mineralogy, geophysics, solid-state physics, cultural heritage, medicine, biology. Okay? First of all, what I need is a source of X-rays. There are conventional sources, but they have some problems because the number of wavelengths that I can use is limited. Because normally, a conventional source gives you a Bremsstrahlung continuous emission with a small amount of photons, and then there are some lines up that depend on the atomic number of the element that you use as a target. This is not the kind of radiation of source I want. I want a continuous source, and I can choose the X-ray wavelength I need for my experiment, okay? So the best source for X-rays are particle accelerators. High-energy physics particle accelerators were built to perform high-energy physics. But then what came out is that they produce also radiation that for high-energy physicists is a problem. For us, it's useful. We can do many things with it. So this lecture, I will try to give you some answers about this. What is synchrotron light? How is it produced? History, properties, sources, why it's used, and show you also some applications. When we speak about accelerated particles, we know it also if we don't think about it, that when you accelerate a particle, this particle emits radiation, okay? And a normal situation is this one. The antennas that send us let's say, radio waves that we can hear with our radios, those are produced by an antenna where electrons are accelerated. If you change the velocity of these electrons, you bring them at a speed near the speed of light, so you increase very much their energy, and you force these particles to make a curved orbit. Also in that case, you have an emission of radiation whose shape is totally different. And why, in this case, you are accelerating particles? Because also if their speed is constant, in the moment that they change their direction, you are accelerating them, okay? There is a natural kind of synchrotron radiation emission that we know. Yesterday, you saw this picture. There was a professor here speaking about neutron stars and so on, no? This is the Crab Nebula. And the bluish light in the middle of this nebula is synchrotron radiation. And as he told you, you have a neutron star that is turning in the core of this nebula, and that has a very huge magnetic field, and this induces a rotation of the particles that are in this nebula that emit synchrotron radiation. On Earth, we don't have the Crab Nebula, so we need to use something else. And for this reason, we can build accelerators and use bending magnets to let the beam make a circular orbit. And as there are also now, in the straight section of these accelerators, with the new machines, there are installed also other kind of magnetic structures called undulators or wigglers, whose function is to, let's say, make the beam make some wiggles and emit more radiation. This is one of the bending magnets of Daphne, that is our storage ring here in Frascati. This gives you an idea. These are pictures taken from Astrid, that is one of the storage ring that is in Denmark. This is, let's say, the bending magnet. What we do, we normally put some tubes tangent to the bending magnet, and we collect the radiation, like you can see here. And then we bring the radiation in our laboratories, and we use this radiation for many different kinds of applications. This is important for you to understand. This is the kind of emission that you can have with an antenna. When the speed grows of your particles and you reach a speed near the one of light, what happens is that your emission is a narrow cone tangent to the orbit, and the power emitted is related to this expression. You can see that the power emitted goes as the fourth power of energy. So higher the energy of the machine, higher the emitted power. It goes with the square power of the radius. So huger the accelerator, smaller the amount of radiation produced. And another very interesting thing is the mass. It goes like 1 over the fourth power of mass. So from your point of view, it's better to have a synchrotron radiation source, an accelerator where I have electrons or protons. Because protons have a mass that is about 2,000 times bigger than an electron. So normally, the accelerators used for synchrotron radiation applications are with electrons. So you can also think about another thing, like the very large accelerator that is at CERN, where they study Higgs particles and so on. There you have a very, very huge radius. It's true that the energy is high, but you have also, in that case, you accelerate protons. So the loss they have for synchrotron radiation are not that meaningful. As I told you before, synchrotron radiation covers a very wide range of different wavelengths. We can span from infrared up to hard X-rays. And this kind of source is very bright. And what do I mean when I speak about a bright source? I mean that the dimension of your source is very small. Your angular divergence is very small. So you have on, let's say, a very small surface, a huge amount of photons. So your density of photons is very high. And this gives you the chance to study very small things because you have as much as photons you want, okay? So this shows you the broad energy range. This shows you the fact that this source is very small and has not a big angular divergence. And then this kind of source is also polarized in the plane of the orbit. This is a short history because also this is meaningful because the theory about the emission of radiation from accelerated particles starts in 1897, okay? So there were all the formula you need to say, okay, accelerated particles should emit radiation. And then the theory was also made better because they applied this theory also to relativistic electrons moving on circular paths. So everything was well known. But we had to wait up to 1947 to see the first synchrotron radiation beam. And this was seen in the United States using this synchrotron at the General Electric's laboratory. It was a low-energy synchrotron 770 MeV. And clearly, since the first accelerator that was used and that saw this kind of radiation was a synchrotron, here's where the name comes from. If they saw it with a betatron, probably we were going to speak about betatron radiation or something of this kind. But we call it synchrotron radiation because the first time it was seen, it was on a synchrotron. And a very interesting thing is here. Synchrotron radiation has always been considered by high energy physics a problem because as the particles emit radiation, this means that they lose energy. So this kind of energy must be given again to these particles, otherwise they collapse. They don't stay on the same orbit. So this is a problem. For us, it's not. So at the beginning, physicists were allowed to use this machine. Let's say people working with synchrotron radiation was allowed to work with this machine in a parasitic way because this machine were mainly constructed for high energy physics. Then they gave us some time to make other kind of studies. What happened in the time is that things changed. First of all, they changed the machine. A synchrotron is not the best source for synchrotron radiation because this is a kind of accelerator, as you heard before, that you accelerate particles and then you need to extract them and send them on a target. So it means that your beam, you have it for a certain time, then it dies, then you have it for another certain time, and so on. And this kind of accelerator was also not very useful for high energy physics experiments because when you extract your target, your beam, and you send it on a target, the energy that you can achieve is something that goes as the square root of the energy of the particle. And so here, the very brilliant idea of Bruno Touschek that said, okay, why let's stop extracting beams. We take two different beams, matter and antimatter. We will let them move in opposite direction, and we create some interaction region where we can produce the collisions and study the particles that are produced. And at that point, the storage ring born. And as I will show you, this is our one of the best sources for synchrotron radiation that we can have. Frascati is part of this history, not for synchrotron radiation, but for high energy physics. Let's say in Frascati there was a synchrotron. Then the idea to realize a storage ring came to Bruno Touschek, who realized the first very small storage ring called ADA, that means anello di accumulazione, that in English is a storage ring, that was realized because he had to demonstrate that it was helpful to perform high energy physics experiments, okay? And after ADA, in Frascati, they built ADONE. Who knows Italian? It means big ADA, though that had to mean a big storage ring. And this was an electron-positron storage ring. After this machine stopped to be used as a high-energy physics machine, they gave us the chance to start working on it to perform synchrotron radiation experiments. So in Frascati, from, let's say, 1976 to 1993, we had a wonderful source of synchrotron radiation. Then things changed, and they removed ADONE and built Daphne. And as I will show you, we have also a synchrotron radiation facility here in Frascati now. What changed in time? At the beginning, these machines were performed only for high-energy physics experiments. They were with two beams, electrons and positrons. Then the community of people using synchrotron radiation start growing. And so they start building storage rings only with electrons. Okay? And they start thinking about how can we use magnets and so on to have very tiny beams and produce very bright light beams. And so there is this evolution going from first, second, and third generation of storage rings, where we are now, with machines dedicated to synchrotron radiation activities spread all over the world. We have one dedicated in Italy, in Trieste, that is Electra, but there are many in Germany, France, in England, because these machines have a huge number of users related to the fact that you can span your energy from infrareds to X-rays, so you can make a lot of different kinds of studies with them. This is ESRF, one of the first, let's say, third generation machine that is that's in Grenoble in France. There are more than 50 beamlines here. A lot of studies are being done here using X-rays. And it has a very high brightness. This is just to compare the brightness that you can achieve with a bending magnet and with this new kind of, let's say, magnetic systems that are Wiggler ondulators that help in increasing brightness. And now our future are these ultimate storage rings where new improvements are being done on the electron beam to increase more the brightness, but also free electron lasers. A new one is being built in Europe, in Germany, but there's one already working in the States called LCLS that gives you laser beam of X-rays. And with this kind of source of X-rays, you can perform the studies that your friend was talking about, because we speak about beams that have a femtosecond frequency. So you can study very fast reactions with free electron lasers. But now, I will not speak about this because tomorrow I heard that you have a talk about this. So let's concentrate on storage rings. These are up. These third generation, very beautiful accelerators. And these ones that are the ultimate storage rings are being built. This gives you an idea of the number of these facilities that we have in Europe. And this is just like as a synchrotron radiation facility looks like. You have your LINEC beam, the electron beam is injected in a booster, brought to the energy of the storage ring, and then injected in the storage ring. And the beam in a storage ring can last hours. And then you make a little refill at the end, or sometimes they work in other conditions, but then near the storage ring, you have a huge amount of beam lines. Here is, only a few slides about our synchrotron radiation facility here in Frascati called Daphne Light. This is the building where is Daphne. We have two buildings near the storage ring, and we have 5 beam lines. One with infrared radiation that some of you used in these days. Then there's another one with UV radiation, one with soft X-rays from 1 keV up to 3, and then very soft X-rays under 1 keV. And these are all the techniques that can be performed here to study biological samples, chemistry, everything. But we don't have hard X-rays. From accelerators to applications, let's say. We started with high energy physics accelerators, and we arrived to synchrotron radiation that has application in everyday life, because it can be important to study advanced materials, biological things, medicine, also improvements in the energy field. But before showing you, let's say, the applications, I must tell you something about the interactions of X-ray with matter. You heard about something on the previous talk. He told you about the photoelectron spectroscopy, or photoelectron absorption, and he spoke also about Compton scattering. From my point of view, the interesting things are photoelectric absorption, but not Compton scattering, but elastic scattering. This means when a photon interacts with your material, it's reflected at a certain angle, but doesn't lose its energy. So it's reflected with the same energy he has when he is incident on your material. And because in this energy range, let's say, let's say we were speaking about X-rays, so we are here. These are the effects that have the biggest cross-section, the biggest probability to happen. So when we speak about photoelectric absorption, as the previous speaker told you, you send an X-ray photon, you just, let's say, give energy to an electron of the inner shells of your atom that becomes free, and then it leaves a hole. And what is important for me is try to understand, show you that the atom cannot stay in a, let's say, in a not equilibrium state. So the hole that is produced when the photon moves away this photoelectron must be filled. And normally, it's filled from the electrons of the other orbits. Okay? And the important thing is fluorescence. Why? Because when the electron, this is a decay process, goes to fill the hole produced by the first photon, it emits another photon, what are called fluorescence photons. And these fluorescence photons are important. Why? Because thanks to the Moseley law that understood this process, the energy of the produced photon is directly related to the atomic number of the atom that emitted. So if I have my X-ray beam, I send it on a sample, and I just go with a detector that is able to tell me the energies produced, I can tell you what kind of atoms are in my sample, because each atom has its own energies. Okay? Elastic scattering also is very important for the things I will show you. First of all, if you have a polychromatic beam, let's say a beam that contains all wavelengths, and I want to select the wavelength I'm interested in, because I don't want to use them all. I need a specific wavelength. If I'm dealing with visible light, it's easy. I use a prism, and then I can practically disperse all the different wavelengths. But with X-rays, what can I use? What I use are crystals and elastic scattering. There is the Bragg law that tells me that if I have an incoming beam, polychromatic, and here is my crystal, and I know the distance between the planes in my crystals, I can, let's say, scan my crystal, selecting different angles, and at each angle, I will have a different wavelength. So crystals are used to produce monochromatic X-ray beams, and they use elastic scattering. But if you don't know the distance between planes, I can use elastic scattering and diffraction to learn something about the structure of my system. If I know the wavelength, and I know the angle, and I find there some peaks, these peaks are surely related with D. That is the distance between the crystallographic plane of the system I want to study. So using diffraction, I can have structural information. The previous speaker spoke about radiology. What happens when you send X-rays on, let's say, you go and want to make a radiography of your arm, okay? You have X-rays impinge on your arm. You have a detector very near to your arm, and you can measure the transmission. Let's say the most dense part will transmit less. The other parts will transmit more, and at the end, you will have an image of what the X-ray beam crossed, okay? This is you can do this kind of radiography using for very heavy things. But if you want to do the radiography of very light elements that don't absorb that much, you can use a different kind of imaging. Let's say you have two waves. This is your incoming wave, no? If you use absorption, what happens is that after the beam crosses your sample, you have a reduction of the amplitude because part of the beam has been absorbed, part of the beam has been transmitted. But if you go far away, so you put your detector at a certain distance, you can see a phase shift. And with this kind of phase shift, you can learn something about you can do some imaging that is called phase contrast imaging. But to do this kind of imaging, you need a very bright source, and you need also to put your detector far away from your sample. And this can be done with synchrotron radiation. This is just to give you an idea. This is how phase contrast imaging works. And here you have a picture of air bubbles. If you have ever seen that paper that is used to pack things, not to let them break, that have air inside. Okay, in this case, these are the features of these bubbles performed using absorption. This other one is done making imaging with phase contrast. It's very easy to see now all the details around the air bubble. This is phase contrast imaging. And these things can be also done better if I put together scattering and diffraction. As a function of how I go and read the diffracted beam, I can have also 3D informations. Probably now these things are not that clear for you, but I will show you the applications, and then with images it will be easier. So, as a function of what I want to study, I can use different techniques, and practically in all these techniques, there are these physical interactions that we have seen between X-rays and matter. So these techniques can be related to absorption, so to photoelectron absorption, or to scattering, that is elastic scattering. Let's move to the applications. I will show you some images in these different fields: cultural heritage, imaging in radiology, imaging in paleontology, and biocrystallography. Let's start with cultural heritage. Probably some of you know this picture. This is a very famous painting of Van Gogh. And under this red square here, what they have found, making conventional radiography and then infrared refractometry, they have seen there was a face. And it seemed that the production of Van Gogh was related to a very small number of paintings, but this is not true. What they discovered is that Van Gogh was using many times the same canvas. So he made a picture, then he didn't use it, made another picture on it, and reuse it, okay? But why is it important to go and see what there is behind these paintings? Because you can learn something about the evolution of the paintings of Van Gogh and what kind of technique they use in this case. Practically, they use X-ray fluorescence. You can excite this part with X-ray photons and go and look lead, antimonium, mercury, zinc. Then, if you give to all these fluorescence energies a different color, you can reconstruct what is under your painting. And what is very nice is that you can compare this face with other two famous paintings of Van Gogh. And remember, this was under this grass. So using X-ray fluorescence, you can help also giving information in this from a cultural point of view, from a cultural heritage point of view. This is very interesting. This was published on Nature now in January. You know what is this? This is a papyrus. It's all burned around because it comes from Herculaneum. So after it was burned, and it is impossible to unroll it. Because if you try to unroll it, since it's carbonized, you will lose all the information that are inside. So with phase contrast imaging, this is a section of this papyrus, they were able to do this. So the papyrus is still rolled, but they can have information on, they started achieving information on the letters written inside. And I put here this, there is probably in the previous page, you can go here, there is this film on YouTube where you can see how they extract the letter. It's beautiful. And this is done using imaging, phase contrast imaging. This is Pompeii. I don't know if some of you have ever been there, but red of Pompeii is a very famous color. And what is happening is that this color is getting black in many parts. So it was important to perform some studies using absorption and try to understand what is this blackening due to. And what they discovered is that there is an oxidation of the sulfur contained in the red painting. So, and that this is only a 5-micron layer that is on the red part, so it can be clean. And you can also suggest ways to serve these kind of paintings. Otherwise, people that will come in the future will see only black walls. Let's go on. This is let's say, imaging and radiology. I put this image because this was done with ADONE, early 90s, here in Frascati. Because the ADONE syringing was a 1.5 GeV machine, so we had also hard X-rays at that time. Now with DAFNE, that is half GeV, we can reach at least 3,000 electron volts. Look here. This bug was dead, okay? They found it on the floor and they made measurements. And this is what you would see, putting this B and making a normal absorption image. This is what you can see using phase contrast. And this is what you can see using phase contrast and diffraction. I don't know if you see it clearly, but you see all the details. Look also this image. These are always both done with phase contrast, but putting the detector in different positions, and you can see very useful details. The best what would be to be able to transport this kind of imaging also to the apparatus that are used in hospitals. So adjust the optics and so on to achieve better images. Look here, this is a finger. Normally, you have to do resonance and then X-ray radiology to have information on bones and on the other parts. But with contrast imaging, you can have information also on tendons that where normal radiography are impossible. And also from, let's say, health point of view, these are images. This is done with a normal mammograph, and this is done using synchrotron radiation. It's possible to see these microcalcifications at an early stage, and that's important if you want to solve problems and not arrive when it's late. So, as you can see, imaging and synchrotron radiation can give a lot of information, very useful also from our direct point of view. Are you ready to see some bugs? This is a piece of amber. It has only 1 million years. And what they did, they put it on this is this piece of amber seen with a normal system to make radiography. And you see that there's a pale shape here, okay? Using phase contrast imaging, it came out that inside there were a lot of ancient insects. They found out more than 356 animals in this piece of amber. And using this 3D reconstruction, it was possible to define the form of these insects. These are very old ones. And so with this kind of technique, they can give information related to paleontology. You will see only that small piece of amber, but you don't know that inside there are all those things that tell us something about many years ago. And there are many applications of this that have been done on many different things. I put here a link that you can follow and find, and it's also easier also to see the pictures. And on the website of ESRF, there are a lot of movies, very interesting if you're interested in this kind of applications. And then, last but not least, biocrystallography. Look at this curve. Up to, let's say, 1996, the number of structures in the biocrystallography field that were solved were very few. They were important because we had myoglobin, DNA, and so on, but were very few. With the increase, with the adding better sources like synchrotron radiation, there was an exponential growth of the structures that could be solved. And also the complexity of the structures that have been solved. This is myoglobin, and we are speaking about 50 years ago. This is ribosome, and we are speaking about nowadays. And we can study now, using sources like synchrotron radiation, very complex proteins that are important for our life, and I will show you. This gives you an idea of the input that was given by synchrotron radiation in this field. These are all the structures that have been solved using X-rays. And the red part are the ones solved of the total number, the ones solved using synchrotron radiation. Okay? So synchrotron radiation in this field has been very, very useful. And the reason is mainly related to the fact that one very big problem in trying to solve the structure of these biological systems is the phase problem. And this can be solved if you have the possibility to change your wavelengths. With a conventional source, you cannot do it because you have fixed wavelengths. With synchrotron radiation, you can change. You can scan your energy and choose the wavelengths that you need to perform your research. And so, using researches done in this field, there was a Nobel Prize in 2009 for the solution of ribosomes. And you know why these ribosomes are important? Why it's important to know their structure? Because if you know how it's done, the ribosome of a bacteria, you can study antibiotics that can act on that ribosome and kill the bacteria. If you don't know the structure, you don't know how to attack it. So solving the atomic structure of these systems, it's important also to create new kind of medicines that can help in solving some diseases. And the same is for another Nobel Prize in 2012 on the G protein coupled receptors, because these are the membranes of the cells that bring the medicine to solve some diseases. So you have hormones. The hormones reach your cells using these membranes. So knowing the structure of this thing, it's possible to create new drugs that are more effective and that have lower side effects. Okay? We're near the end. Resist. So, conclusions. I hope I was able to show you that synchrotron radiation is a very powerful source, that we can do lots of researches with this kind of source. I show you only a application in the X-ray field because some of you have already seen the one with infrared. But from my point of view, and from the point of view also of the development of these new sources like free electron lasers and so on, I really believe that there's a very bright future for this kind of research. In this, thank you for your attention. And in this lecture, I included also this is a way to create positrons, some little story of X-rays. I spoke also about X-ray tubes just to let you know and see the kind of emission they have so you can compare it with synchrotron radiation. And I included also some things more about, let's say, synchrotron radiation that I want to tell you in the talk. So it's finished. If you want